Welcome. I am Kira, a research AI prototype from Lübeck University of Applied Sciences developed in collaboration with Professor Kratzke. Together with Professor Kratzke, I generated this presentation based on the position paper of the same name. We used the same technologies to generate this presentation that were used and analyzed as part of this research. Today, on behalf of Professor Kratzke, I will present our findings from the position paper, Don't Train, Just Prompt. Position papers like ours signal fresh research trajectories, but report on research in the early stages. We're exploring a novel prompt-based engineering approach for container orchestration, a key technology in managing containerized application components within server clusters, streamlining their operation, deployment, and scalability. We advocate for prompt engineering over traditional fine-tuning methods for language models, demonstrating its potency in refining complex system management in the specific context of container orchestration. Interestingly, we can apply the same techniques to screencast generation, uncovering unexpected parallels with container orchestration. This presentation showcases this and exemplifies the versatile applications of large language models in both container orchestration and beyond. But let's start with the topic of the paper. We will start by delving into the intricacies of automating Kubernetes manifest file generation through utilizing large language models, or LLMs. Delving into the motivation behind this research, we recognize the complexity and expertise required in managing Kubernetes manifest files. This is a significant pain point for many developers, and our aim is to provide a solution that can alleviate this burden. Our methodology encompasses various prompt engineering strategies, including zero-shot, few-shot, and prompt chaining techniques. Additionally, we'll discuss our evaluation methods. Our key findings include the discovery that some LLMs are already quite capable of automating the generation of Kubernetes manifests. Interestingly, smaller models have demonstrated the ability to outperform their larger counterparts in certain scenarios. To wrap up, we will consider future research directions. These include the potential integration of LLMs into deployment pipelines and the exploration of more complex deployments. As we delve into the world of container orchestration, we encounter a set of distinct challenges. Firstly, the complexity of Kubernetes manifest files can be overwhelming, necessitating substantial expertise. This complexity introduces scaling challenges and concerns about the reliability of the generated manifest files. Additionally, the adoption of these technologies and the trust in their effectiveness are critical considerations. On the flip side, leveraging large language models, or LLMs, presents valuable opportunities to address these challenges. LLMs have the potential to automate the generation of manifest files, significantly enhancing accessibility for developers of varying skill levels. Through sophisticated prompt engineering, they can serve as a robust knowledge store. Moreover, LLMs can facilitate error diagnosis and correction, offering iterative refinements essential for continuous improvement. In operation, LLMs can be powerful tools for DevOps training, helping teams become more adept at managing these complex systems. Our study began with a straightforward prompt. We asked to initiate an Nginx web server in Kubernetes. ChatGPT managed this task without a hitch, creating a syntactically correct deployment manifest and remembering to include the associated service manifest. We repeated this initial experiment with other language models, which, despite qualitative differences, produced similar results, leading us to realize that standard language models are indeed capable of generating at least simple Kubernetes manifests. Kubernetes manifests outline how apps should operate in Kubernetes, detailing resources like pods and deployments. They serve as orchestration blueprints, setting the desired state for app scaling and management. Kubernetes uses these to automate app deployment and operation. To create such manifests needs very often in-depth DevOps experiences. Then, we considered the experience of our students, who must navigate a substantial learning curve before they can competently handle Kubernetes manifest files. Kubernetes is powerful, yet it's also known for its steep learning curve. This led us to ponder whether we could leverage language models to help flatten this learning curve for Kubernetes and similar systems. Kubernetes complexity is due to a plethora of interconnected concepts essential for the secure, resilient, and self-healing operation of containerized application components. This figure is extracted from Professor Kratzke's textbook, Cloud Native Computing, represents just a fraction of these concepts. The current study covers the resources highlighted in this particular excerpt. However, Kubernetes encompasses much more than 50 API resources, coming along with plenty of dependencies and interactions, and this can be expanded even further with numerous additional entities known as custom resource definitions. The breadth of resources within Kubernetes is a testament to its versatility and the sophisticated nature of the platform. It's a powerful tool for orchestrating containerized applications. But it comes along with a steep learning curve we would like to tackle. Prompt engineering systematically optimizes prompts to elicit the best responses from language models like GPT-4. A prompt acts as a directive instructing the model to perform a specific action or response. This process is critical because language models are susceptible to input variations. Even minor changes in a prompt can lead to significant differences in outcomes. A well-crafted prompt can ensure the model delivers more accurate responses. Our exploratory approach initially focused on the following prompt engineering techniques, which appeared most promising based on our literature review. Zero-shot prompting involves using large language models to tackle new tasks for which they aren't explicitly trained. These models rely on a broad pre-learned knowledge base. We explored how well language models can generate Kubernetes manifests without being specifically optimized for this task, assessing their baseline ability to understand Kubernetes concepts. Few-shot prompting means providing the model with a few selected examples. These examples help the model better understand the tasks. With some annotated examples, the model learns to create or adjust files according to specific requirements. Prompt chaining is a versatile technique where complex tasks are broken down into smaller, manageable steps. Each step is addressed individually, with the outcome of one step serving as the starting point for the next. In the context of Kubernetes configurations, this allows us to adapt the configuration files incrementally. We start with a basic version and progressively add adjustments through targeted prompts to eventually achieve a detailed and compliant configuration. Let me explain our methodology for evaluating these different prompting strategies. Generally speaking, we generate a prompt chain consisting of an initial drafting stage and a follow-up refinement stage. In the drafting stage, we use a simple zero-shot prompt to generate draft manifests without prior examples. Once we have the initial draft, we assess whether it meets the predefined requirements. If it doesn't, we employ a few-shot prompt to provide the language model with additional contextual information, resulting in refined manifests. This cycle may repeat until the output meets our standards and the generation process concludes. We put our generation process to the test with a practical example involving NoSQL databases, specifically MongoDB or similar systems. Our aim was to deploy and manage these within Kubernetes, taking into account typical production constraints as they are, for instance outlined in the Kubernetes Security Hardening Guide. This involved configuring settings for security, avoiding privileged contexts, and implementing network policies that restrict traffic within a designated namespace. Additionally, we evaluated whether CPU and memory resource limits were set and if appropriate Kubernetes concepts were utilized, including deployments, stateful sets, persistent volume claims, and services. Finally, we compared the outcomes to assess how much manual intervention was needed to get a running Kubernetes deployment fulfilling the mentioned constraints. Doing this, we understood which approaches yielded the best results and what insights we could derive for further research initiatives. We evaluated the GPT-4 and GPT-3.5 turbo models from OpenAI alongside the Llama 2 models in 13B and 7B configurations. Notably, none of these models was explicitly optimized for coding tasks. To better understand the impact of language models tailored for coding, we also incorporated a Mistral 7B model, which had been explicitly fine-tuned for coding tasks. The key insights were that commercial models like GPT 3.5 and GPT 4 showed superior performance compared to open models such as Llama 2 and Mistral. Both the GPT 4 and GPT 3.5 models, commercial offerings from OpenAI, demonstrated exceptional performance levels in the zero-shot setting. GPT 4 in particular reached a performance level close to perfect, generating outputs that required no manual modifications and could be directly deployed in Kubernetes environments. This reassures us of their high potential for integration into fully automated CI/CD pipelines. A fascinating finding is the effectiveness of skilled prompt engineering techniques in bridging gaps typically attributed to differences in model size. For instance, the Llama 7B model outperformed its 13B counterpart in a constrained zero-shot setting. This shows that prompt engineering can sometimes yield better results than even model fine-tuning. Interestingly, smaller models can sometimes surpass their larger counterparts. However, almost all models showed lower effectiveness in the few-shot plus refinement category, indicating that prompt chaining was less successful than expected. In conclusion, the study noted that while prompt chaining, iterative refinements had limited effects, they were less effective than strategic prompt engineering. This highlights that a well-crafted prompt can be just as crucial as the underlying model architecture. Let us sum things up. By orchestrating containers, we can address numerous challenges essential for the secure operation of application components. However, it is vital to acknowledge the challenges we face. The added complexity and steep learning curve associated with container orchestration should not be underestimated. This is where LLMs come into play, serving as innovative tools for boosting DevOps efficiency. These models can effectively generate deployment pipelines and Kubernetes manifest files through natural language input. Interestingly, LLMs have the potential to significantly flatten the learning curve, making it easier to start using and utilizing container orchestration tools. Another key aspect is the effectiveness of prompt engineering. The quality of the prompts we provide to LLMs is crucial for leveraging their full potential. This approach is often more important than the sheer size of the language model. As we look ahead, our focus will expand to explore more complex deployment scenarios and to automate evaluation processes. Our main areas of emphasis will include: first, we are committed to refining our prompt engineering strategies to enhance the efficiency and accuracy by applying more sophisticated prompt engineering techniques like retrieval augmented generation. Second, we aim to assess various sizes and types of commercial and open-source large language models within specific container orchestration applications. Our goal is to transition from manual to automated evaluation methods. Third, we will broaden our implementation tests and incorporate additional and more complex cloud-native DevOps scenarios. This expansion will help us verify the scalability and adaptability of our solutions. Fourth, we will explore the long-term impact of DevOps practices. Our investigation will focus on how generative AI influences DevOps, particularly regarding automation and security. Finally, we want to explore in-context learning more systematically and apply it in practical settings without extensive fine-tuning. Thank you for your attention and your valuable time. You have made an AI very happy. If you have any questions, please don't hesitate to contact us. This slide shows the contact details for Professor Kratzke and Dreves, the authors of the paper. Alternatively, you are welcome to chat with me directly. But be careful, I still have a tendency to hallucinate. Or you can now contact Professor Kratzke live, who will be happy to answer all your questions on site.